Hi, I'm Mobile from Auburn High School, and I'll be presenting my project, Resolving Warping of Thermoplastics in 3D Printing via Analysis of Potential Solutions in this video. Firstly, we have the outline of this presentation. I'll be going over the background, research questions, hypothesis and engineering goal, materials and instruments, experimental design and procedure, results, and conclusions of this project. So, this project aims to research and resolve warping in thermoplastics, the most utilized material group in 3D printing. But what is warping? Well, warping is a common issue in 3D printing and occurs as a result of material shrinkage during printing, causing the corners and sometimes more of the part being printed to lift and detach from the build plate of the 3D printer. This is bad because it results in the deformation of the 3D print, rendering it useless in some cases. Thus, warping wastes time, energy, and money while also producing trash, and so resolving it is important. There are some problems with existing research on warping. They offer no convenient solutions to the problem, as they only involve the adjustment of material and part-specific 3D printer operation settings. Meanwhile, help websites do not delve deep into warping or address the effectiveness of provided solutions. Therefore, the research questions for this project are: how will factors and potential solutions affect warping of thermoplastics in 3D printing, and what solutions are most effective in resolving the problem? My hypothesis is that the force of material shrinkage causing warping can be offset through adjustments to 3D print's surface area coverage, shape, environmental temperature, and material. In doing so, warping can be resolved. The engineering goal of this study is to establish general solutions and determine the critical operation parameters, particularly the area, thickness, and shape of the 3D print for low-cost efficient fabrication of various shaped thermoplastic parts without warping brims. On experimental design and procedure, this chart and these steps are all the necessary information. After conducting the experiments and gathering the data, I could finally analyze it. The formula used during this experiment was warped proportion is equal to warped volume over volume printed. Elaborating on these values, warped volume is the empty space which the warped material would have occupied, and volume printed is the volume of the part printed out. Now, this measurement is only accurate on parts that did not detach from the build plate of the printer, and using it, the following table was able to be completed. To read this table, there is some important info. The cells under surface area coverage trials each represent a part and contain the dimensions of the surface area coverage. The cells under shape trials each represent a part and describe the shape of the surface area coverage. I would like to point out that the square shape trial is actually just a 12.5 by 12.5 centimeter trial. Additionally, trials which are marked with an asterisk are where the part detached completely from the build plate. So, starting with the surface area coverage trials, despite the 10 by 10 part having a lower warp proportion than the 12.5 by 12.5 part, it actually experienced complete detachment from the build plate of the 3D printer, meaning the warping it has was greater than that of the 12.5 by 12.5 part. Given that, there would be a trend where the greater the surface area coverage of a part, the lesser the amount of warping it experiences is. Then, moving on to the shape trials, where all parts have the same amount of surface area coverage but as different shapes, we can also see a trend. The more corners a part has, the lesser the warping it experiences is. Finally, we have the materials test, where PETG showed promising results by having a warped proportion of 0%. I even printed a triangle part with PETG, and it still experienced no warping, though that isn't listed on this table. Now, moving on to the solutions tested. Generally, bed adhesive reduced warping the least, while the heat enclosure reduced warping the most, if excluding brims. However, when including brims, they consistently perform better than the previous solutions, being able to completely resolve warping in some cases. PETG and PVA performed equally well as brims, completely resolving warping, while PLA performed slightly worse. TPU was the worst at preventing warping, but even then, it reduced warping more than solutions using adhesives or the heat enclosure. We also have graphs to visually represent the data. As we can see again, warping is lower in parts with more surface area coverage in corners. From these graphs, we can see that the bed adhesive consistently prevented the least amount of warping, while the heat enclosure prevented the most. Finally, we can see that PETG has the highest resistance to warping out of the materials tested, and additionally, PETG and PVA brims prevented the most warping out of the brims tested. Here are some photographs showing warping in different parts. Starting from left to right, with no intervention at first, there is a big amount of warping. Then, when adhesives and heat enclosures were applied, it was reduced to a small amount of warping. But finally, with the help of the brim, no warping occurred. From the data collected, we can make the following conclusions. Adhesives are budget options to resolving warping, while heat enclosures, despite costing more, will produce better parts and offer a long-term solution. Meanwhile, brims are produced with just the 3D printer itself and the filaments, all of which are already used when 3D printing. Increasing the surface area coverage of a brim will in extension increase the resistance to warping of the part the brim supports. Additionally, a brim's shape can be customized, and designing it to be less angular will spread out the force of warping, thus increasing resistance to warping further. Finally, a new method of reducing warping, which this project introduces, is printing a part consisting of one material with a brim made of a different material. This allows a material with stronger resistance to warping to introduce its properties to a part in the form of a brim. This project showed that the material of the brim a part is printed with does indeed impact the amount of warping that the part will experience. Ideally, the brim material should be rigid enough to provide support, having some level of roughness to increase grip and adhesion between the brim and the part, while maintaining some flexibility and/or resistance to stress. These factors present in PETG and PVA allow the two materials to perform extraordinarily well as brim material. Whichever material a person chooses to print a brim with will simply depend on their preferences and needs. This project has useful applications, having demonstrated that it is possible to completely resolve warping with straightforward methods, making it useful to the various fields of 3D printing. Finally, future directions include focusing on fabricating complicated structures of biodegradable PLA scaffolds. Here is the bibliography for my project. I hope you enjoyed this presentation, and thank you for your time.